Hello. I'm going to continue talking about the data link layer. And what we were talking about in the last video was error detection codes. That is the way to put parity bits onto what we send to allow us to detect perhaps a 1-bit error. The cyclic redundancy codes, which were the last part of what we mentioned in that video, can detect much more. The mathematical theory tells us what kinds of errors it can detect. I'm not going into details on that. But now I want to go to a slightly different kind of code. Can we send a message in such a way that not only can we detect a 1-bit error, but we can find which one it is? So the message does not have to be resent. We can correct it on the receiving it. There are many codes to do this. Perhaps the easiest is the group of codes known as the Hamming codes. It's actually a group of codes because we can use different size messages that we send. I'm going to do one example of it and perhaps another one afterwards. Now, the Hamming code, the way to understand it is we start with a message of a certain size. And what we're going to do is add more than one parity bit. What we're going to do is add parity bits based on the binary representation of the bit number where each of our bits that we're sending are. So in this table below here, first, notice surprisingly I'm starting at 1. I'm not starting at 0. I have bits 1 through 15. And what I'm saying is, look at them in their binary representation. Bit 1 is 0001. Bit 2 is 0010. That's 1, 2, and nothing else. This is 1 times 2 plus 1. That's 3. This is 1 times 4. This is 1 times 4 plus 1 times 1, or 5. So all of these can be represented that way. Now, here's the trick. I'm going to take every one of these positions that has a 1 in the 1 column, the 2 to the 0 column, and I'm going to put a parity bit on them. Then I'm going to take every one of the bits that has a 1 in the 2 column, 2 to the 1, and I'm going to put a parity bit on them. And then I'm going to do the same for 2 to the 4th, 2 squared, 4, and 2 cubed, 8. I'm going to put the parity bits in the locations that are where the bit number is a power of 2. This is 2 to the 0. This is 2 to the 1. This is 2 squared. This is 2 cubed. I'm going to put the message bits in the other places. So I'm going to start by saying, since we have 15 of these, and we need 4 check bits, we're going to be only able to send an 11-bit message. That is the message part. The actual code we'll send will be 15 bits. So let's suppose I want to send 100, 101, 10011. The first thing I do is line these up in all the places in a 15-bit word that are not powers of 2. So I put the 1 in 3, bit position 3, the 0 in bit position 5, the next 0 is 6, 7, the 9, 10, 11, 12, 13, 14, 15. So those bits are the ones in the message. Now I look. Take every bit position that has a 2 to the 0 in it. 1 times 2 to the 0. Now, coincidentally, not quite completely coincidentally, those are the odd positions. Look at what you have there already. We have 1, 0, 1, 0, 1, 0, 1. That's 1, 2, 3, 4 ones. I want to work with odd parity. I can control this bit. It's not part of the message. So what I do is I put a 1 there, so I will have 5 ones in all the bit positions that contain a 2 to the 0. Now I look at 2 to the 1. I look at all places that have a 2 in their representation. Now you got to be careful here. This is not the even ones, and it's not the ones that are 2, multiples of 2, because this first one, for example, is 2 plus 1. And this one here is a 2 plus a 4. This one's a 2 plus a 1 plus a 4. It's just, is that third bit from the left, or first bit from the right, or however you want to look at it, is that a 1 or not? So I bring down to this group here, all of those. This I have to put in. I put it in already, but I have to look at the other ones first. I have a 1, a 2, a 3, a 4, a 5, a 6. Well, it looks like I need another 1 to make it a 7 for an odd parity. So I put a 1 in the 2 position. Now I repeat this for all bit positions that have a 4 in their representation. So there's the pure one, 2 squared. Then there's 5, 6, 7. 8, 9, and 10 don't. Neither does 11. But 12, 13, 14, and 15 do. So I put those in. I get 1, 2, 3 ones. So the parity bit I place in there is 0. And then finally I do the same thing for all that have an 8 in their bit number. Now that means 8, 9, 10, 11, 12, up through 15. I look at the bits I already have, 1, 1, 1, 1. That's 4 ones. I have to put a 1 in to keep the parity. So I now have the message I send is 1, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1. I am using 15 bits to send an 11-bit message, which means that I only have 11/15ths of the bandwidth that I can use for the message. 4/15ths is used for the check bits. All right, well, that's the theory of how I set it up. What good is it? How do we figure out where the error is? All right, suppose 1 bit changes. Then every one of these rows where that 1 bit is has changed parity. And every one of these rows where that 1 bit isn't haven't changed parity. So I recompute the parities in each of these rows. So I did this on the next page. There's what we receive. Now I look at this. Okay, I look at all the ones up here, and if you'll notice, this one's different. This will be a 0 now. So the 2 to the 0s have a parity. The bit that has changed is in the 2 to the 0 group, the 2 squared group, and the 2 cubed group. So each of those will have odd parity when we can calculate it. We know then that the bit form must have a 1 in it, it must have a 1 here, and it must have a 1 here. The 2 to the squared group hasn't changed. So wherever there's a 1 in the 2 to the 2 group, everything's fine. So XX1X hasn't changed. It's still okay. So that means that the bit that is bad must have a 0 in the 2 to the squared group. 2 to the 1 group. So putting all this together, I have 1101. Another way of looking at it is to just add together the powers of 2 for all the groups that no longer have odd parity and work it out that way. It's a relatively simple approach, and I said as a member of a group, we've just shown one possibility. But now let's suppose I'm willing to send 31 bits. So if I want to use 31 bits to transmit a message that can have a 1-bit error detected, corrected by Hamming methods. I chose, by the way, 31 because, I'll say suppose. Suppose I want to do this. Now, I chose 31 for a very important reason. If you look at all the numbers we have, 1, 2, 3, I won't put all of them in, blah, 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 blah. And then I'll say 30 and 31. Now let's look over here. I will give you now the 5-bit representations of those bit positions. So put over here bit position in base 10, and over here bit position in base 2. That's pretty easy. 0, 0, 0, 0, 1. 0, 0, 0, 0, 1, 0. So far it doesn't look different than what we had before. But now let's look at 30. Okay, let's see. 30 has a 16 in it. That's 2 to the 4th. It has an 8 in it. 16 and 8 are 24. It has a 4 in it. That brings us to 28. It has a 2 in it, and it has a 0. So if you add all those together, you will get 30. And then down here, we have 1, 1, 1, 1, 1. So it's the same as it was before, except we have another group, the group with the 2 to the 4ths. So if we were going to make up a table for this, we'd add another row. Look at all the places with 2 to the 4th and put an odd parity on them. Now, we need a parity bit for let's see, 1, 2, 4, 8, and 16, those groups. So we need five check bits. This is called Hamming 3126. What that means is I can have a 26-bit message and send it with 31 bits. This means we have a 26-bit message with 5 check bits. So now, a minute ago we said that we were 11/15. Now we're 26/31. Well, what are those two numbers? I don't feel like doing arithmetic, so let me open up a new one over here. So here we have 16 and 11. Here, not 16, 15 and 11. Over here we have 31 and 26. So this is 11. This is G5 divided by F5, 73%. And if I continue this down here, now I got 83%. If I add one, if I go to 63, I'm going to need 6 check bits. So that means I have 57 that can actually be used to send the message. And now, if you look, it's getting better. Of course, as I have more bits, I get more chances of them changing, and more than one changing. So it's not perfect. But it does produce a way of doing things. There are other error-correcting codes. I'm not going to pretend these are the only ones, but I think this is the one that's most easily understood. The others can get quite complicated. In fact, for most of the others, I have to immediately get into matrix theory to make them work. And I didn't think I wanted to do that at this point. The point I'm making is that security is extremely important. And we have developed all kinds of ways to check messages to see if they get there properly. If you look at your Wireshark, you'll see that there are CRCs that are sent. So this is not unusual. We're willing to spend the extra bandwidth to take care of checking things. That's it for now. I'll see you again shortly.